last chunk of section 2 is integrating trig functions. And up until now, we have learned the integral of sine and the integral of cosine. And we just sort of define those for you from taking derivatives from earlier in the year. So we know that the integral of sine u is cosine u, but we have to make it negative because the derivative of cosine is negative sine. We know that the integral of cosine u is sine u, and that one is positive because the derivative of sine is cosine. And then we know that we have to include the plus c's on there. But what about the other ones? Tangent, cotangent, secant, cosecant. We haven't talked at all about those. No, you don't. Just skip that one, for sure. So the 4 remaining integrals, these guys right here, when we integrate those are best found now using the log rule, not using the front of your book. Just yet. So we're going to learn 2 of them and show you how they come about. The others are in the book for you, like actually worked out somewhere, but then the front cover would be the best place to go for that. So, one of them's easy, one of them's not quite so easy. The integral of tangent x, we're going to rewrite as what? Yeah, tangent is sine over cosine, so this is sine x over cosine x dx. Now, based on what I've just said about we're using identities and log rules, what might we do here to integrate this?
We could get u prime over u.
Okay.
So we would need negative sine.
U prime over u. That means the derivative of the denominator needs to be sitting in the numerator.
It needs to be negative sine.
Yes. The derivative of the denominator, cosine, is negative sine. We almost have that here. We would if we just had a negative sign right there. So if I put a negative sign out front, that keeps this thing in balance. And now we have u prime over u. So what do we get?
The negative natural log of absolute value of cosine.
Don't forget your plus c. So that's the answer right there, using the log rule, which is kind of nice. Now we've derived the integral of tangent. And we can apply the chain rule to that, or chain rule looking things, and make it tangent u du equals the negative natural log of cosine u in absolute value plus c. And the absolute value symbols are necessary there. For secant x, that one's a little bit tougher. What we're going to do with secant is wind up having to multiply by a fancy 1. The fancy 1, or usually like you would think of an identity or something. In this case, we're going to trick this one by multiplying it by a fancy 1. And the fancy 1, don't ask me how they came up with this one, but the fancy one is secant plus tangent. Yeah. So, like I said, don't ask. Secant x plus tangent x. Why? I said don't.
I know, but how are you thinking about it? You said no.
Because what they're trying to do is they're trying to get this into a form that we can take the derivative of. So we're trying to get the derivative of the denominator into the numerator. So there are some identities that involve secant squared and secant squared plus tangent, so we'll get to that in a second. Oh, is it already ringing a bell? Okay. So we have now the integral of, if I send in the secant x into the top, then I have secant squared x plus secant x tangent x over secant x plus tangent x dx. So now the question is, what do I do from there? Just turn everything into something else?
Even tangent?
No. The derivative of the stuff on the bottom, we need to have it on the top. So we need to
Okay, so Yeah, let's remember what the derivative of secant is. This sounds like a job for the inside cover of your textbook.
The inside cover of your textbook.
Derivative of secant is secant tangent. The derivative of tangent is secant squared. So if I take the derivative of the denominator, what do I get? The numerator. So actually, by multiplying by this fancy one, I created u prime over u. For no reason. All right, so we have the derivative of the denominator sitting in the numerator, which means I can integrate this, and what do I get? Don't forget your plus c. And that is the answer. So now take a look in the front of the book and see what the integral of secant x is. Or it'll say secant u. There you go. So the trick was this fancy one right here, and that's how all of these integrals go. If we were to look at cotangent, cosecant, and that's it, cotangent and cosecant, they work the same way. There's some sort of fancy one or some sort of identity that they use to convert things around so that they get the u prime over u. And once they do that, then here is your list of all of your trig functions being integrated. Sine u we knew, cosine u, we knew that one. Tangent u we just derived. Secant u we just derived. And then these two guys here are derived in very similar fashions. So I'm going to skip those, but that's where they come from. The absolute value symbols on these guys are necessary because obviously we can have positive and negative values in those trig functions. You need to be familiar with these and with the trig identities listed in the front cover and the back cover of your textbook. I think actually now they're in the front cover, right? Yeah. So, on the AP exam, what are you expected to know? Yeah. None of them are off limits on the AP exam, but typically you're only going to see a few of them. Sine and cosine for sure are on there, and maybe one of the other four. So here's an example involving area underneath the curve of a trig function that we don't typically see. So y equals the square root of 1 plus the tangent squared of x is this graph over here. And we want to find the area under the curve between the y-axis and the line x equals pi over 4. So the y-axis forms this side, and then pi over 4 is here. And then we want the area under the curve, and then also with the x-axis. So we're looking at this area right here. Now, in order to find that area, obviously we're going to have to integrate that guy, right? The problem is we don't know how to integrate something that looks quite like this. The nice thing is we might have some sort of identity or something that would let us convert that. Do we have a nice identity conveniently that would allow us to convert that to something that we can integrate? One plus tangent squared is secant squared. So I can convert this then, and now I have y equals the square root of secant squared x. That is just secant. So we wind up with just y equals secant. So now I can integrate secant x dx. Is that the graph for secant? No. Why does it do that instead? Secant usually looks like this. No, there's no absolute value up there in that function. But what did happen? Somebody was muttering something. Yeah, the tangent squared part makes everything positive. So now you're guaranteed to be positive here, so that when you take the square root, it's still positive. So effectively, it was an absolute value situation, but that's why we don't have this bottom part, and now it's just all bounced up here instead. Okay, so we have the integral of secant x is equivalent to what we're dealing with here. What else do I have to do?
We have to take into account the other bounds.
The bounds? What are my bounds?
0 to pi over 4.
Okay. Now what? Now we integrate it? Good. So what is the integral of secant x?
Only we did this.
The natural log of u plus c.
Natural log of,
The absolute value of u plus c.
so secant x,
Plus tangent x.
but we're evaluating a definite integral, so we don't have to put the plus c. So there's no negative sign out front or anything? That's it? Oh, is there?
Why?
That was tangent. Tangent had a negative sign out front. Okay. So this,
Yes, everything I know.
this is from 0 to pi over 4. Now what?
Now we plug in down.
Plug in stuff. Okay. So the natural log of the absolute value of secant pi over 4 plus tangent pi over 4 minus the natural log of the absolute value of secant 0 plus tangent 0. Okay, so this is the natural log of the absolute value of secant pi over 4. What is secant? Which trig function are we talking about here? Okay, 1 over cosine. So at pi over 4, we need cosine. Okay, but it's 1 over.
So 2 square root of 2 is square root of 2.
Yeah. If you think about, so you get 1 over the square root of 2, really. That's why we wind up with the square root of 2 over 2, because we rationalize the denominator. So if I go back to this look right here, then when I find secant at pi over 4, I just flip this and I get the square root of 2. Anyway, this is the square root of 2. What's tangent pi over 4? Yeah, it's 1. Square root of 2 over 2 divided by square root of 2 over 2. So 1. So I have plus 1 here, right? Not minus 1. This is secant x plus tangent x? Oh, okay. Minus the natural log of the absolute value of secant 0. 0. Is that right? I heard a 0. Secant 0. Secant is 1 over cosine. Cosine at 0 is 1. So we have 1 over 1, which is 1. Plus tangent 0. Now it's 0. All right, so we have the natural log of the absolute value of the square root of 2 plus 1 minus the natural log of the absolute value of 1. Do I need the absolute values anymore? No, because I have a positive and a positive here, and I have a positive here, so I don't need absolute values, and I don't need my calculator just yet. Natural log of the square root of 2 plus 1 minus the natural log of, that was supposed to be a 1, looks more like an absolute value.
The natural log of 1 is 0.
The natural log of 1 is 0. So my actual exact answer is the natural log of the square root of 2 plus 1. If I need a calculator approximation at this point, I can type that into my calculator and get an answer. So let's go ahead and do that. 3 decimal places. I have no idea. Something small. 0.881. What was the 4th decimal place? Okay, so 0.8813, which means my answer is 0.881. That's the approximate answer. Okay, find the average value of that function on the interval, that interval. What is the most important thing that's said in this problem?
The average value.
Thank you, the average value. How do I find the average value of a function over an interval? Right.
So I did learn something more.
So let's go ahead and try that.
I think Nosey's right.
Talk me through it.
I don't want to get 5.
Get 3, get 5, get.
So use the average thing, so B minus
1 over b minus a.
A. I'm already get a star. Keep it up. I'm going to go on the functions.
From a to b of the function dx. That's a good place to start, especially if you're taking an AP exam. It takes 10 seconds to write it down, and you let people know that you know what you're doing. So next, what do we have?
1 over B minus A.
1 over b minus a is
1 over pi over
1 over pi over 4, which becomes
4 over 5.
4 over pi. Integral,
From 0 to pi over 4.
good.
Outstanding.
If only we knew what that integral was.
Hey, we do know what that interval is. Negative.
You sure it's negative?
Natural, yes.
So 4 over pi times,
Negative natural log of the absolute value of cosine x.
Value.
just cosine?
Evaluated. Evaluated from 0.
Good, from 0 to pi over 4. Okay.
So we do that.
All right, so we do that. What do we get?
Bring the negative out.
Ugh. 4 over pi. I'm going to leave that negative alone because I'm not confident in pulling that negative out there. So I'll leave it there.
So negative natural log of cosine of pi over 4, which is square root of 2.
Okay, and then therefore do I need the absolute values? No, so we have negative natural log of the square root of 2 over 2. Then, it will turn into plus. The natural log of cosine at 0 is 1, so natural log of 1. This is 0, so minus minus 0, doesn't matter. And now I have 4 over pi times the negative natural log of the square root of 2 over 2. So as a decimal, 0.4412. So 0.441 to 3 decimal places is your answer. Nice job.